In 6.6, our objective is to use proportionality theorems with triangles and parallel lines and calculate segment lengths. Use proportionality theorems. Remember that last time we talked about how to know when two triangles are similar. Let's look at this picture. Are the triangles shown similar? How do we know? Well, what triangles do we see here? Maybe we draw them separate from each other. I see a triangle that's QSR, so I'm going to draw that separate from the picture, QSR. And I see another triangle inside that triangle, TUR. So it's a little bit smaller. I'm going to draw it separate from the picture, TUR. Well, what do we know also from the picture? This length from Q all the way to R is 2 and 5 put together, so that's 7. This length in the picture from S all the way to R is 3 and 7.5, so that's 10.5. And in the little green triangle, TR is 5 and UR is 7.5. Well, remember our three similarity postulates, theorems that we can check. Angle, angle, side, 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 or side, angle, side. Which can we use here? Well, first of all, I don't know the third side in either of the triangles, so side, side, side is out. I don't appear to know any angle measures, but remember that these two triangles came from being inside of each other and both used angle R. So angle R is congruent to itself by the reflexive property. It's the exact same angles, so I have that and that. So perhaps I can try to use side angle side and see if these sides that include that angle is proportional, if those sides are proportional. But it's actually quicker if we just notice that we've got parallel lines here. See these arrows? They tell us that these lines are parallel. Therefore, we have a pair of corresponding angles up here and a pair of corresponding angles down here. I don't even need those because once I know that angle Q and angle T are congruent to each other, now I've got angle, angle. One pair of congruent angles up here, a second pair of congruent angles down here. So by angle, angle, we just proved that these two triangles are similar by angle, angle. Well, what if we wanted to use side, angle, side? We could have done that too. Let's look at the sides that correspond, the small side with the small side. Well, what's 7 over 5? Well, that doesn't reduce, that's 7 over 5. How about we try the long side, 10.5 over 7.5. Type that in, that reduces to the same fraction, 7/5. So side, side, side can also prove that, not side, 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 sorry, side, angle, side can also prove that these two triangles are similar. Either way, we want to do it, angle, angle, or side, angle, side. We do see that triangle QSR is similar to triangle TUR by one of the postulates or theorems that we choose to use. Well, what I want you to see today is that by knowing that these are similar triangles, we can match up these corresponding parts, but it came from the fact that we have these parallel lines that are right here. See these parallel lines that are marked? That's telling us a lot about the picture. So I should erase them. So we can always match up the corresponding sides of the triangles, but in a picture like this, without even splitting it up into triangles, there's other types of corresponding parts that we can match up. Let's just take a look at something else besides the sides of the triangle. We matched up the entire side 7 to the entire side 5. Those are the smaller sides. But what if we look at this picture as a whole and match up just pieces of the sides? What if we match up this little piece that's on top with this little piece that's on the bottom and make a ratio from those pieces? So 2/3. 2/3 does not reduce to the scale factor of 7/5. Remember, when we match up the corresponding sides, that gives us the scale factor, and 2/3 is not equivalent to that scale factor. But it shouldn't necessarily be because it's not a side of a triangle, it's a piece of a side. We did the piece that's on the left with the piece that's on the left, going from top to bottom. What if we match up the piece that's on the right with the piece on the bottom that's on the right. So we did left with left, and what if we do right with right? Well, let's make into a ratio those two pieces on the right, 5 and 7.5. Let's find our calculators and type it into there. So I'm going to use this calculator because it's easy to make a fraction with this one. 5 divided by 7.5, and we can either enter right there or we can go straight into math and frac, and we see 2/3. Well, let's go back to this and see that's the exact same ratio we had from left with left. So the point here is the parallel lines gives us more opportunity to match up corresponding parts. What if instead of going left over left and right over right, what if we go in a different order? Let's try another pattern. How about left to right? So let's do 2/5. Not the same ratio that we had before, but that's because we're going in a different order. Instead of top over bottom, we're going left to right. Now let's do that on the bottom, left to right. 3/7.5. Let's go back to our trusty graphing calculator, and 3 divided by 7.5. We'll go straight to math, make it a fraction, and 2/5 is what we get, 2/5. So you see, going in an organized manner, left to right, we got the same ratio again. So this shows us that we may have similar triangles in which we can use the entire sides, but because of the parallel lines, we also now have corresponding pieces that are proportional. These parallel lines are dividing these sides proportionally. Let's write that down on your note sheet because that's going to be what's very useful for us today, is that we start with, and this is in your picture already, we start with lines being parallel. If a line is parallel to one side of if a line is parallel to one side of a triangle and intersecting the other sides, so it's parallel and it intersects the top side, intersects the bottom side, and it's parallel to the left side, then what happens? It divides the sides proportionally. It divides the sides proportionally, divides them proportionally. So that means we don't need to take the entire side. We can go in an organized manner to make a ratio, left top to bottom. So I could say, I could write QT over SU equals, and then on the right and on the right, again going top to bottom, going in the same direction. That would be TR over UR. Or we saw also going left to right, as long as we do left to right on the other part of the picture. So we could also say QT, this piece right here, and TR, this piece right here. That ratio is the same as the ratio going left to right, SU over UR. As long as we follow the same direction we did on the other side of the triangle. Lots of ways to make the proportions. Now the converse of this triangle proportionality theorem is also true. Converse meaning we flip this around, starting with the conclusion, if the sides are divided proportionally. So if we start by seeing that these proportions are true, this side over this side equals this side over this side, or some sort of proportionally divided sides, then the line dividing will be, well, what do we start with over here? Parallel. Then the line dividing will be parallel to the triangle side, the triangle's side. Let's look at some examples to see how this can work for us. In the diagram, this tells us segment AB is parallel to segment CD. So that's shown in the picture. AB is parallel to CD. BD is 15. So I'm going to put that in the picture, 15 for BD. AC is 10, so AC, put 10. CE is 18. CE is 18. Find DE. We'll put X there because we don't know it. We can make a proportion because we know these lines are parallel. So we can make a proportion that goes top over bottom, left only, 15 over 10. As long as we follow the same order on the other side, top over bottom, X over 18. Not the only way to do it, but a way that will work. We could have done left to right, so 15 over X and left to right equals 10 over 18. Either way we choose to do it will work because we're going in an organized manner. How do we solve this? Well, it's best that we simplify it first and then we can cross multiply. 15 tenths simplifies into 3 over 2. So let's rewrite this as 3 over 2 equals X over 18. We can cross multiply from here. If you prefer to use a property, go for it. 2X equals 3 times 18, 54. And dividing both sides by 2, X equals 27. Well, they said find DE, so I will write DE equals 27. Let's look at the next one. In this diagram, segment PQ divides sides LN and MN into the lengths shown. Determine if PQ is parallel to LM. Determine if they are parallel. We don't know that PQ is parallel to LM. That was not given. We're trying to figure out if they are parallel. That's the converse of that proportionality theorem. Let's see if the sides are divided proportionally. So if we go in an organized manner, little piece on the left, we could put with little piece on the right, going left to right. So that would put 18 over 27. The question is it equal to going left to right along the bottom, 16 and 24? Little piece on the bottom, little piece on the bottom, left to right, as long as we're going in the same order. Is it equal to 16 over 24? Well, one of the best ways to do it is reduce both sides, see if it works, or maybe we cross multiply. So if we were to reduce both sides, 18 over 27, this divides by 9 and makes 2, this divides by 9 and makes 3, this divides by 8 and makes 2, this divides by 8 and make 3. So yes, they are equal. We could have checked it this way. 18 over 27 equals 16 over 24. We could have checked it by cross multiplying. What is 18 times 24? What is 27 times 16? Are they equal? Let's see. Clear out. 18 times 24, 432. 27 times 16, 432. So we see that both of these are 432. They're equal. Either way we choose to check it, it shows that the sides are divided proportionally. Therefore, determine if these lines are parallel. Yes, we will say PQ is parallel to LM. So similarly to having triangles that are divided with parallel lines, it doesn't have to be triangles divided with parallel lines. It can be actually any lines that are divided with parallel lines. So in this picture, let's show that this is parallel to this and to this. So these three lines are parallel. This is called the three parallel lines theorem. If the three lines intersect, if three parallel lines intersect two other lines, we'll call them transversals, then they divide the transversals, those lines they crossed, proportionally. So we can make proportions. If we've got parallel lines crossing, we can make proportions. So again, in an organized manner, we can do UW over VX, go top to bottom. So if we go UW over VX, what's going in that same order? How about WY and XZ, top to bottom? WY and XZ, top to bottom. Well, that can also equal the whole length on the top and the whole length on the bottom. Again, going in the same direction, UY over VZ, as long as we are going top to bottom because we started top to bottom. Find an organized way. Match up corresponding parts. That's the biggest thing. Match up corresponding parts. Let's try a little practice on the next page. Feel free to pause this, come back, check your answers, see how you did. Use the figure to complete the proportions, complete them. Given we've got three pairs of parallel lines, parallel, parallel. So this is parallel to this and to this. B, C, D, E, F, G, three sets of parallel lines. Let's talk through these. AB over AF. Here's AB, here's AF. So it went little piece, but both are on the top. So this is a top, but this is the little piece. This is the top, but this is the big whole way across. What does it show us over here? BC. BC is a little piece. And it's not on the top this time. Where is it now? It's on the right. So this is on the right, and this is little. So if we went top and top, little to big, now we're on the right. Well, we want to stay on the right. Little to big, little to big. So on the right, big part on the right, F to G. See how that works? Want to try a few and come back? Let's do more. AD over BD. AD, BD. So we went AD, AD, BD. Then AE, and then what? So we started on the top, larger piece to smaller piece, and then went to the bottom, larger piece, follow it with smaller piece. We go big to small, we stay in the corresponding order, big to small. So CE fills in that blank. Let's take a look at a similar theorem. The last one we're going to talk about today, triangle, angle, bisector, proportionality theorems. So this is a picture of a ray bisecting an angle of a triangle. This is making two congruent angles. This ray is bisecting it. Let's write down that. If a ray bisects an angle of a triangle, what happens? Because of similar triangles, and we can take a look at that proof in class, because of similar triangles, it divides the opposite side into segments. So the opposite side is this side, it divides it into segments. So here's a segment AD, Here's a segment BD. It divides the opposite side into segments, and those segments are proportional to the other sides. Here's what that means. These two little segments, the side that's divided opposite the bisected angle, so those segments are AD and BD, will have the same ratio as the other sides put together. So AD is the segment on top. We'll go with the side that's on top, AC. BD is the segment on the bottom, so we'll go with the side that's on the bottom, BC. Let's take a look at some examples that have numbers. Solve for the missing side length x. So I see the bisected angle is here. I look across from the bisected angle, this segment says 3. I look across from the other bisected angle, this segment says x. That has to be equal, if I went bottom or top to bottom, then I do the ratio of the sides going top to bottom, 9/12. And then we can solve that proportion. I like to reduce first, so let's reduce it. 3/x equals 9/12 reduces to 3/4. And without even cross multiplying really, I see both numerators are 3, therefore both denominators must be the same as well. X must equal 4. Now I could have set this proportion up a different way. So let's look at it in a different way. Instead of going 3/x, I can do little segment that's on the top with side that's on the top. So little segment over side. 3/9 equals, as long as I go in that same order, x/12. Let's see if it works out the same. Well, first of all, 3/9 reduces to 1/3. And now if we cross multiply, 3x equals 12. And dividing by 3 gives us x equals 4, just like we did the first time. Why don't you try this next problem, pause, and come back, see how you did. So this is a little bit different in the way that it's drawn, is just because they don't give you this segment length. So across from this bisected angle is x. What's across from this part of the bisected angle? This piece right here doesn't say anything. So we see that the whole way across is 8. This part is x. So this leftover part is the whole way across minus the little piece next to it. Once we've labeled this, now we can make our proportion. So little segment x over little segment 8 minus x, the segments across from the bisected angle, equals, now I went top to bottom, so staying in that same order, I will go top to bottom, 3/9. Again, I like to reduce. I'm going to do a couple other properties besides reducing. So 3/9 reduces into 1/3, but if I also use my reciprocal property and write this as 8 minus x over x and 3/1, then I can use my addition in the numerator property. I see x down here, so I can add it to the numerator. I see 1 down here, so I can add it to the numerator. How is that helpful? Minus x plus x, the x's in the numerator go away. 8/x. 3 plus 1 is 4, 4/1. Now I can cross multiply. 4 times x equals 8 times 1. Dividing by 4, x equals 2. Good job.